Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to the today's lecture, and delighted to introduce to you Dr. Schultz, who's a senior lecturer at University of Hertfordshire near London. And this is, as Bodo, what the senior lecturer means, is basically the position before you can be before the full professorship. And Dr. Schultz received his bachelor and doctorate degree, and this advanced degree that's equivalent of super PhD from University of Kiel. Habilitation. Yeah, habilitation. And I asked why he stayed the same place. He couldn't resist not racing on the sea. Right. So today, Dr. Schultz will tell us about SaC, Single Assignment C.
Yeah. Thank you very much for the introduction, and thank you very much for the opportunity to give a talk here. Actually, the talk is about work that we have been doing since about 10 years, but it has obtained a new spin to it by the introduction or the advent of multicores or many cores. So essentially this talk is a wrap-up of the work that we have been doing so far, and trying to give you an insight or share the insights that we have gained by doing that, and give you an idea of what we are currently doing. As you can see, it's not a single man effort. Over the time we have gathered quite a crowd who has contributed very much. Maybe I should mention in particular Clemens Grelk, because he joined very early and is one of the key contributors in this framework. Okay, let's talk about what is this new spin all about. Well, most of you are most likely aware of this. There's much talk going on about getting into the multi-core business. Today our software runs on single cores, and the multi-cores are now entering the mass market. You'll get a dual core for your desktop, and the quad core is on the horizon, and what have you. But if you think about the software, then essentially it becomes increasingly more difficult to actually make use of this. Well, dual core is still kind of simple. You know, you think of a GUI and you spin off a few threads and that's fine. Maybe quad core as well, but what do you do if you have hundreds of cores? So then you could say there are the pessimists around and say, well, you know, 50 years of research, and where are we? Where are our parallel tools? This is a dead end. We are never going to solve this problem. You know, what is our predominant programming language? It's Visual Basic, or it's C or Java. And if you want to have parallelism, then we go MPI or OpenMP. Why is that so? Couldn't we do any better? Well, my claim, my very personal claim, is partly that is due to the fact how we use the parallel system so far. Because we were interested in HPC. So people that actually were using it were throwing lots of money because they demanded the utmost performance. So just think of it, if you have a company that is spending millions of dollars to buy a machine and millions of dollars to run the machine, then they are prepared to pay lots of money to programmers that are really, really skillful to get the last drop of performance out of these machines. And I want to refer to these as black belt programmers because I like this term. I think it's very figuratively. Now, well, why wasn't it adopted in the mainstream then? Well, if you really needed more performance than you could get on your today's desktop, then you just would have to wait a couple of years, and then you would have a machine that does it. So there was no real point to parallelize algorithms there. And that's, I think, one of the major reasons why we still see not a mass market suitable tool for actually programming these machines. So that is actually setting up the scene for what we try to position ourselves in now. So what do we want to address? We do not want to address the black belt programmers that squeeze the last bit of performance. Instead, we are looking at the white belt programmers, at the people who are actually interested in the application. Primarily, they want to get the program run. They want to understand the program. It should run fast. They are not really interested in programming concurrency, telling the machine where to squeeze in a certain thread, how to synchronize things. They're not really interested in whether it is a cell they are using, or a Cyclops, or just a GPU. They want to write their program and concentrate on that. What kind of architectures are we targeting? Well, let's go hand in hand. If we look at this kind of programmer, then we definitely do not want to go for dedicated HPC machines as you can see them in the national labs. Instead, we're thinking of the machines that are cheaply available, if not now, then in the near future. So we are thinking of the SMP multicores like the dual core you have right now on your desk. We are thinking about maybe using GPUs for this purpose, because they are not really expensive. And then there are a few more advanced architectures like the cell, or if you look at ClearSpeed's T-Export, or even the upcoming IBM Cyclops machine. Now, if we want to address this setting, then still we want to make use of the achievements of parallel research into parallel programming. So what do we have? Well, if we look at the mainstream languages, then my rather radical term would be we are in deep trouble here. Because what do we have? Well, there has been lots of effort put into getting automatic parallelization running. I would hope to get some insights and some success stories to believe in this. I don't. The few times I tried to do that were disastrous. It never really worked. And if I wanted to get it work, then what I had to do is I had to study carefully the manual of the compiler and then find out, oh, maybe I have to put a pragma here, and oh, maybe I have to reformulate it here, and then maybe it works. But that is not suitable for the white belt programmer. By no means. And if you start going into this route, like manual parallelization, you have to synchronize things. Anybody who has ever written an MPI program knows how steep the learning curve is and how much misery you have to go through to get it really right. So,
I think the third point is actually what summarizes it, that the programming language community, I don't want to address them only, has not found the right abstractions that help us as the average person to make this parallelism easily available.
Well, if you, for example, you could say, maybe I should have elaborated on that more. If you look, for example, at Java, then you have some abstraction there. But still, I'm teaching courses in Java and exactly doing that, and you wouldn't believe what kind of errors you can make. So it is by no means easy. However, myself having a functional background, this is a very important question here, saying, can functional languages live up to their promise? Can they really do better? And if you ask people from the community, which I'm including myself in, then we would say, yes, of course, we have Church Rosser and everything becomes better because all the concurrency is explicitly there. We don't have to infer it. Well, if you look at it in practice, then yes, we do have the concurrency available, but it is very difficult to tell which concurrency actually you want to use, because it is very difficult to tell what kind of granularity are we dealing with. So if you look at the exciting examples that we have in the past, you can see that essentially people come to the conclusion, well, we have to have some form of annotation. We have to find a way actually to tell the compiler where the concurrency is worthwhile for exploitation. And so we have evaluation strategies, and more recently the software transactional memory, where you can actually do this a little bit better. However, that requires you to have insights on your concurrency. And that means the white belt programmer has not just to focus on his application, but he has also to think about how to exploit the concurrency. So,
the future is one of the example of the annotations. Right? future, the language construct, it's one of the annotations that
you could have, yes.
And what are the annotations?
Well, you have, if you do, so for example, you can introduce par constructs, which then are maybe exploited by the compiler, or you could, if you talk about evaluation strategies, then you could say, well, this is a parallel map that should be exploited. So you can attach to the data structure that you want to do something as in forms of a higher order function. This is really, it's really nice work that has been done there from Simon Peyton-Jones and others.
Well, in general, these higher order functions give you the ability to decide that there is parallelism in there.
Yes, but again, it requires you to have this insight in your program. It requires you to...
If you write a map, the programmer doesn't know whether or not...
That is true, but if this is not, the evaluation strategies are to actually make the maps that you want to exploit explicit.
Oh, I see. So meta-programming.
It is kind of a meta-programming. But the nice thing is, in a language like Haskell, you can do that in the language itself. So I still think, programming should even be more easy than that. I think we should really try to liberate the programmer from any concurrency concern, at least on the surface. Is there anything? Well, obviously, I claim, yes, there is something. I believe in the data parallel approach. It's not a universal solution for everything, but for a certain kind of applications, very, very well suitable. And we have a couple of developments there, Sisal, Nestle, single assignment C, as I will talk about a little bit more, and more recently, the data parallel extensions of Haskell.
May I ask a slight comment to that?
Yes?
I'm from a database community, so I would say we do this for 15 years already on a different granularity level. But I mean, look at databases. They live off parallelism on data partitioning for a long time already.
Yeah, I'd love to have a chat with you, because I actually think that our model would be very suitable to express certain data mining applications. So what is our basic idea? What is our approach? We have chosen to call our language single assignment C because we essentially had the idea that we want to take a language that looks like C, feels like C, but still is functional. The reason for that being that we thought we have to lure people into trying our language. So rather than asking them to adopt something completely different, they would have a smoother transition. How can you think about it? Essentially, it is an extension of a subset of C. And if I say subset, all I mean is get rid of pointers. While getting rid of pointers may seem a lot, because it effectively betrays you of all data structures. However, all the other constructs you can leave in the language, syntactically unaltered. Then we have a purely functional subset, which we're dealing with, and we decided actually to not integrate any of the nice frills you can have with functional languages like Haskell. So we don't have lazy evaluation, we don't have type classes, you don't have polymorphism, just the very basic stuff. However, we integrate a very powerful generic programming model for n-dimensional arrays. So in a way, as a replacement for the pointers, you now have arrays, very powerful arrays. And what we want to do is we want to do compiler-directed exploitation of these operations on large arrays. Now, how do we approach the entire task? First of all, we say we are not general purpose, we are restricting ourselves to certain application areas which are suited to the model of computation in mind. And this is primarily, as we thought when we started, scientific computing and image processing. However, more lately, it became clear to us that actually it is much more diverse what you can do with this kind of approach. You can actually do very well financial modeling that has been done since ages with APL and descendants. And actually, I very strongly believe in the possibility to do something in the field of data mining, and that's why I find that in particularly interesting input here. Another thing which is in the foreground of our design is we said we actually do want to have a very high level of abstraction. And we want to be able to write very generically applicable functions and operators and combine these to write actually programs. And that is very similar to the way you would write an APL program to some extent. However, we do not want to have this bulk in our language where we have millions of different operators which have a predefined meaning. We strive for an as lean as possible design. Not just for pragmatical reasons, but also just because we believe that a language that is to be adapted needs to be reasonably simple. So why does it have to be functional? Surely not for exploiting the parallelism that comes out of Church-Rosser directly, but more importantly, we want to have it in order to be able to radically optimize our programs. And we will see later that this is actually absolutely key to that. And then obviously our main goal is we want to compile to multi-threaded codes on SMP architectures.
Can you dwell a little bit more on the question why you decided for arrays and not, for example, for sets, which would be I would say even higher level abstraction, because it leaves out order, and order very often is non-essential.
Because we believe that the array models are more powerful. And I hope that in the course of giving you an introduction to the facilities in our language, I can give you an idea why we come to this belief.
So the functional programming community does sequences or lists or streams. You are doing matrices, and database people believe in sets.
Yes, and we are not doing matrices. We're doing arrays. And
okay.
I'm very happy that you said this, because this gives me a very nice transition to the next slide. So what I try to advocate here is, for the rest of, I don't know, for the next 40 minutes or so, please try to come along and think arrays. Omnipresence of arrays. Everything is an array. Well, obviously, the first thing that springs into mind, and I had just the proof of that, is that if I say array, then people think of vectors and matrices, maybe of tensors, but what's all the fuss about, right? Well, if you look behind the scenes, or if you look into the APL community, then you get other ideas. The first idea that you get is, which may sound strange, is, well, scalars are just arrays. It's just a special form of arrays, but they fit very nice into the picture. Then you also can think about a very, as I would say, whole meal approach to programming on arrays. So what I want to do is I want to actually have operations that take arrays and compute new arrays. I don't have this view of a large chunk of memory which I can address, where I have inherently an order. But I have the idea that there is a structured object here, and then I map it to another structured object there. And even iteration spaces can be arrays. So in fact, you can actually replace recursion by operations on arrays, which is a little bit strange in the beginning, but once you get used to this kind of thinking, it, in my view at least, is very nice. Just to give you a few examples. Up here we have factorial. No recursion visible here. It's all hidden in this operation iota. What does iota do? Iota takes an argument and creates an array, a vector in this time, of the length n, and contains all valid indices in it, which is, in our model, since we're C-based, 0 to n minus 1. Then I add 1 to this array. Adding a scalar to an entire array is defined as element-wise addition. So the result of this is actually the vector 1, 2, 3, 4, etc. to n. What is the product? Well, the product is essentially a fold with times. So our recursion is gone, or has been hidden, in actually this generator of the indexing space. Let's think about L2 norm. So what is the L2 norm? Well, essentially, if I think about it having a vector here, a vector A, then I have the element-wise squares. I sum those up into a single value, then I take the square root of it. Done. Very nice. Definitely no errors in indexing here, because we don't have any. But you can actually propel this style of thinking or programming into much more complex things. Like here we have a convolution step, something that is used over and over again in numerical codes when it comes to solving PDEs. What do you have to do? You have to build weighted sums of neighbor elements.
What?
Weighted sums of neighboring elements. So instead of thinking element-wise, you can also start thinking array-wise. So instead of actually picking the right neighbor element, I can take the entire array and shift it to the left. Likewise, here I shift the entire array to the right. Then I multiply this shifted array with the weight that I'm interested in, and eventually I sum up the entire thing. A very nice specification. And definitely no errors in the indexing. Another example. We test the convergence of two arrays A and B. So what do we want to do? We really want to actually see whether at any position of this array the absolute difference is smaller than a given epsilon. Well, here we are. This is an array, another array. We build the difference. It's an array of differences. We take the absolute value of that. That is the absolute values of the individual elements. Then we compare it against the scalar value epsilon. That is, we now obtain an array of Booleans. And then we have this all operator, which is nothing but an AND reduce. That is, we all combine, fold them with an AND operation. And again, no explicit indexing. So how is the mechanics of this thing? Let's look at the L2 norm again. Let's look at applying the L2 norm to a vector, 1, 2, 3, 4. Now what is happening, actually the L2 norm is expanded to its definition. We have the square root of the sum of the squares. And then we successively apply the individual operations. We start with a square. That means we now obtain the vector of squares. Then we build the sum. That is, we sum up all these elements. And eventually we take the square root.
But you see, you don't use the property that arrays give you ordered elements. You actually could have done it with sets.
Yes. And if you want to look at our arrays as sets, you can do so. Nothing is stopping you from doing that.
In some sense, you are over-constraining yourself and therefore limiting your possibilities in order to do parallelization. That's what I mean.
Example of stencil computation.
Some order is important. I agree.
So I would be interested in seeing why I'm over restricting myself and where. And I would
talk about offline. Yes.
I would like at least to pose it a little bit later, because I think that some of the slides that you will see will give you an idea that we are trying to get rid of these constraints. Now, why is this an interesting example? It is an interesting example because so far I haven't told you anything that this really needs to be a vector. So what is preventing me from actually throwing a matrix at this? Well, then the obvious question is, what is that supposed to mean? Well, and that is very nice, because you can actually say an n-dimensional array can be considered an n-1 dimensional array of vectors. Right? And provided, oops, that wasn't interesting. Anyways, provided that the underlying operators are defined properly, then this actually works. So let's look at this. We are now throwing a matrix at this L2 norm. Whoa. So we have the unfolding of the definition of L2 norm. Now we have the square. Square is defined element-wise. Again, we're not making use of the structure. I agree on that one. So we have now here this matrix 1, 4, 9, 60. Now we come to the sum operator. And the sum operator is defined in such a way that it always operates on the innermost axis. And here we're now making use of the structure. So essentially what is happening is we're building the sum of the vectors of rows. That is, we now obtain a vector here, 5, 25. And then we again take the square root and we're done. Why is this an important feature? Well, it means that the code that I have written having vectors in mind can now be all of a sudden implicitly applied to huge arrays of vectors. And that is what we refer to as shape-generic programming. That is a property which makes code very reusable, provided, because I see your disagreement here, partially at least, provided that these individual operators are built in the way you want them to be. Sure.
They're in some sense polymorphic.
Well, what is generic programming about? It is about polymorphism in a certain way. So, what do we need in order to do this? First of all, we need to have rank n arrays. We want to have support for arrays where possibly we do not even know the rank of the arrays statically. Then we want to have something else. We want to have something like generalized selection. So we want to be able actually to select entire subarrays from a given array. We definitely need to have functions that take entire arrays and return entire arrays, and then we want to have all kinds of these nice combinators. And even better would it be if we could define these by ourselves, so then we can adjust it to the needs of our applications. Well, did I say lean design at a certain stage? Well, this doesn't really sound like a lean design, does it? Well, the good news is, it in fact is, because the crucial conclusion or the crucial idea that we have gained is we can express all this, or most of this, by one single language construct. And that is the power of this approach as far as I see it. So let's go through the individual requirements. First of all, multidimensional arrays. How do we do this? Essentially, if you have a three-dimensional array like here, we have just one set of data in a linearized form here, and we have a shape that we associate to it. In this case, we say we have 2 elements in the first axis, 2 in the second, and 3 in the third axis. And therefore, we can from the shape actually deduce that the rank, that is the number of elements in the shape, matches the rank of the array. Now, if we look at smaller dimensionalities, we can write something like this. Then it's just a vector. A vector means we have just a shape with one element, that is the number of elements in the vector, and the data is just the data vector. How can we complete this? Well, in fact, we can say a scalar is a zero-dimensional array. The shape is empty, and the data vector just contains the value. So it's a very nice closure of this representation. Excuse me. Then I said we need to have generalized selections. And what I mean with that is, well, usually if you think about selections, then you often just want to select a single element. However, if you do that in a conventional approach, then you have scalar selectors. So actually your selection requires as many operands here or indices as you have rank in your array. However, if the rank is not static, then you can't do this. Therefore, we actually use vectors for indicing. And what is particularly nice here is that these are arrays again, because remember, everything is an array. That means we can actually compute these indices with our array primitives. We can apply them in that context as well. Now, if the length of this vector, this indexing vector, actually matches the rank of the array, then in fact it is the scalar selection the same way as we would expect it to be. But if we shrink the length of it, then we say, oh, essentially that would be Fortran-wise, it would be something, or Fortran 90-wise, it would be 0, colon, 1, colon, dot, if I recall correctly, or dot or colon, maybe the other way around. So what it says is we take all the elements in the missing innermost axis. And here we have, so it is here in the front plane, it is the second row, and it's all elements in the second row. If that can be closed again very nicely, so you say if we just have one index here, then we select the entire first plane. That means we actually obtain a 2-dimensional array or matrix, 2 by 3, or if we select with an empty selection vector, then we obtain the entire thing. So, now we have n-dimensional arrays. Now we want to write these operations. We want to define our combinators. And that means we have to be able to actually pass an array of arbitrary shape in here. And to do that, we have to introduce some notion of type here, because we want to adopt the idea to actually declare function types. And what we do is we actually append the base type, the element type that we expect, with shape information. However, if we say this is shape invariant, that is, we can apply it to any array of any rank, then we just use a star. It's kind of, you can think of it as a regular expression, essentially. Now, what does this do? Essentially, here you have the definition in a C-like notation, right? So if we now define our functions in terms of combinators, where do the combinators come from? And remember I said earlier, I don't want to hardwire these into the language. So let's look at this particular example and let's think about the case when these are actually, no, we can't do that, okay. So we start out defining square. However, we first define it on scalar values only. So there you have the standard C definition that you would expect. Now, how can we get this to be applicable to arrays of arbitrary shape and size? And that's where our magic construct, so to speak, kicks in. We called it a with loop. So what it does essentially is it defines a mapping from index vectors to values. And then we, after these brackets are closed here, we say, what are we going to do with all these values? Essentially here we're saying we are generating an array of a certain shape. And by giving this shape, we actually restrict the index domain. So let's have a closer look at just the with loop here. Here is the index domain as we would have, provided that A is a matrix, in fact. We see we have indices starting 0, 0, 0, 1, etc. Down here in the row-wise, the first index increases. The mapping IV to square of A of IV means then simply that the first element needs to be computed as square of A of 0, 0, etc. Notice a few things here. A, the index can actually be used here, which gives us the power to define things like convolution. And second, by construction, since we know that these functions are side effect free, we know that all these computations can be done independently. So in fact, we're having kind of microthreads here. As many microthreads as we have elements to compute. Right? And the generator just tells us what to do, how to compose the entire stuff.
Could you also address elements like A, IV plus 1?
Sure.
But in that case,
the point is,
destructive update analysis. Okay.
the point is, you do not have a handle on the result. You don't have a name of the result. That's why I, on purpose, just looked at the expression here.
What I'm thinking is there would be a huge operational difference, because here you could destructively update probably the original.
Wow. Now you're talking implementation. I'm not talking implementation yet. Essentially what I'm saying is you're computing a new array from an existing one. And in some cases, like in this one, if you have a smart compiler, you can do that in place. But not necessarily. But what is important to notice is I can't really access other elements here. These are per design independent. There is no way to create a dependency here. If you need this and want this, then you can't use this construct.
Can you again explain? I couldn't really get the semantics of the IV again. What is the semantics? What kind of construct is it?
In a way, introducing, if you want to project it to a conventional loop, then you say this is the loop variable.
Oh, I see.
So this is, I'm introducing a variable here which stands for an index.
I see.
And it successively stands for different index. And I'm just, I'm defining an abstract mapping from my index domain to the value domain.
No, I get it.
Okay, now what can we do with this? We have seen that we can extend actually square to do it element-wise on all the elements, but we can actually define our generalized selections by it. Well, that's simple. What do we have to do? let's assume we want to select with an integer vector into a double array A here. Now, what is the shape of the result? Well, the shape of the result is actually the shape of A, but dropping away the beginning extends by as many elements as we have indices here. That is, if we have a three-dimensional array here and we have 3 indices in this vector, then we drop simply the entire shape. And that means this becomes empty. And an empty shape means we obtain a scalar. Remember, we have closed it up, and therefore this now doesn't hit us. If we just have 2 indices, then we are losing the first 2 dimensions. That means, if you think of the example A we just have the 3 elements of the innermost vector. Now this is defining the shape of the result very nicely. Now how do we get, now for a given index here, the value? Again, that is simple. We take the index of the outermost dimensions that have been provided here, and we concatenate, plus is a concatenation construct here, we concatenate the innermost index to it and get the elements we're interested in. Done.
I don't understand this example. Why does job take 2 shapes?
Okay, dropping again is a shape generic operation which takes a vector telling us how many elements to drop in which dimension. However, in this case we're talking a vector here and a vector there. So do we have a, no, we don't have a pen. So essentially what we're doing here, let's think about the situation when we have 2 indices in this vector. Then the shape of this is just the vector containing 2. So we have a drop 2 from the shape of A, and let's assume the shape of A is 2, 2, 3. Then that means we're dropping 2 elements in the outermost dimension. There is just 1 dimension. We drop the 2 and the 2, which leaves us the vector with a 3.
Only for my own understanding, the gen array is more or less telling you what new type you generate out of it.
The generate tells us, we have a mapping here, and essentially the generate tells us what to do with this mapping.
Okay.
And it tells us, create an array whose index space is defined here. We have also different other variants, and I will expose you to one of these here. Let's look at the sum definition, because I think the sum definition actually is a very nice example for the power of the abstraction that we have here. Let's define the summation for a vector. And see here we have a slightly different type, and that just tells our system this is for vectors and vectors only. So what do we do here? We actually, again, have an index space. We are iterating over all the elements of A. We just take these elements and we want to fold them with a plus operation. And therefore, we have now a second variant of with loop which simply takes all the elements it has computed there and folds them into a single value. And here we have to specify the neutral element of that. Now that was piece of cake. Now how do we do the summation on the innermost axis if we have an n-dimensional array? We do it like this. What is the shape of the array that we have? Well, essentially, we just want to apply the summation on the innermost axis. That means we actually have to cut off the last element of the shape of A. That is what we're doing here. Drop -1 of shape of A. And what do we want to do? How do we compute the individual elements? Well, we simply, for all indices in this array, we compute. Here we have a partial selection into A now, take that vector, apply the sum, and that's it. And since this is going to be a vector per design, we will have this function being applied here. Now why is this so interesting? Well, let's think of what I've tried to tell you here. How many data parallel operations do we have? Well, this is a selection here. but it's not a scalar selection, it is a vector selection. So in fact, this is a data parallel construct. Summation, we just figured out this summation is going to be that summation. So this is a data parallel construct as well. Now, how about this? Drop. Drop is defined by with loops as well. So this is a data parallel operation as well. So all of a sudden, we are being flooded by data parallel operations. They're everywhere. They just crept in. You know, like I don't know, mice or something like that. And they're ubiquitous in our program without us really noticing. Because who would think of a data parallel operation if you do a selection? Nobody. Well, not many, maybe. I hope more in the future. Maybe something else I should have mentioned earlier. As you can see, we have twice a definition for the same function name. And what we do is we allow for ad hoc function overloading. All that we require is a certain consistency with respect to the argument types. And here you can see this is defined for arbitrarily ranked arrays, whereas this is defined for vectors. And then the semantics of our language is that you always pick the closest match. And so far, the subtyping hierarchy that we're dealing with is a tree, so that is no problem in this particular case. Now, at the latest in this situation, those people that have been into implementing compilers should start becoming nervous, because in a way it is too much parallelism. How are we going to ever get efficient code out of this? So, what is our real problem? We have a program and we have lots of dinky tiny little with loops hanging around here, which are all nice and data parallel, but how to get them on the hardware architecture? Well, first of all, we have to try to aggregate them. And that is actually something which we can do very, very efficiently, and we have worked very hard to get this done. So what we try to do is actually we try to pull a few of these together and build bigger with loops. Fewer, bigger with loops. There's not enough time here to actually go through all the stuff that we are having. Just to give you a few pointers, 3 major optimization techniques that we have developed. All of these depend highly on the capability to move around code, which is facilitated by the functional paradigm. So if you want to do this effectively, then I do not believe that you can do it without being functional, or at least being sure that you don't have side effects. Now, if the world would be nice, then we would have had to implement just those. However, reality is a little bit different. A reality means, in fact, in order to enable these, we need a total compiler infrastructure. And that is something we did not anticipate in its total cruelty. So it is not just that we need to have all the gaudy well-known optimizations like loop unrolling, common sub-expression elimination, constant folding, what have you. All this needed to be in place in order to facilitate those. But we also need to actually specialize our programs from a shaped generic version to actually shaped specific versions. And to do that, we have a type inference system that aggressively does partial evaluation. So all this needs to be in place to make this happen, and that is required to aggregate our with loops. Once we have done that, unfortunately, our with loop construct becomes more complicated. While an individual with loop usually is rather homogeneous. We have one operation that is being applied to all the elements at the index space. As soon as you start folding these, you get a situation like this. Different colors mean different operations here. So you can have an arbitrarily complex patchwork. Even worse than what you want to have is periodic sets where you want to do something. So you can have these periodic patterns, and then again, due to folding, you can have a mixture of both. So you end up with really, really weird structures that you're dealing with. However, we couldn't care less in a way, because we have the freedom to evaluate these independently. These are still guaranteed to be actually microthreads. Now let's look at how we actually get these microthreads to a real architecture now. So essentially, what we have to do is we have to map these microthreads to real threads. And as long as we don't have these architectures where we have thousands of processes, then definitely we don't want to map each microthread to individual threads. So we have to group them, and there we actually have the liberty to do it in any way we like it. And the way we do that is we try to keep data locality in mind. So we actually say, oh, if we're dealing with these values up here, then maybe we should actually assign them to one processor, because we have, whenever we load a cache line, we already get the data that we want to process next, etc., etc. So the rudimentary approach that we have taken is we actually cut it into n pieces along the outermost axis. Right? So here we have thread 1 and thread 2. We did this static scheduling, and it worked well. However, then we thought, well, maybe sometimes, in particular if these are different operations, you will have load imbalances. How can we deal with that? And the surprising result is that it's rather easy. In fact, it inflicts almost no overhead to have dynamic schemes. And one of the schemes we were particularly interested in is a scheme where we say, okay, we have actually dedicated this to thread number 1, this is dedicated to thread number 2, and then we have some regions which are more loosely affiliated to these threads. And just in case someone has done his and his affiliated stuff, then he can steal, so to speak, parts from the other. However, we found in practice the static scheduling did it for most applications that we were dealing with. Now, how is our execution model actually? It's very, very simple. It's just data parallelism. So we have a single threaded execution here. Then we have a fork, which essentially is entering a with loop. We do the with loop, which is totally independent, and then we have to synchronize again at a join point. And that happens one after the other. Now, the first thing we observed is actually really joining the threads is not a good idea. In particular, if you use p-threads, then this is too expensive. So what we did is we said, in our implementation, we do it slightly differently. We let these threads actually live. The only thing we do is they just wait for a signal to actually go on and process the next second of data. And then more recently, we actually have refined that. We tried to get rid of the synchronization barriers here and there whenever possible by simply replicating the sequential parts of code, following the SPMD model, essentially. Now, is that all? No. Crucial to performance is thinking about memory here. And that actually relates to the question that you were posing earlier, saying, what about reusing memory? What about actually trying to do things in place? In order to be able to do that, we need to know that this is actually the last copy we are dealing with. Nobody else needs to see the old value. And that is only possible by using reference counting, as it's well known from SAC, and there's lots of good work being done there in that context by Ken and others. So we adopted that model. That allows us to immediately reclaim memory, to do actually update and place things. And that gives us the opportunity that we actually allow the programmer to write really ugly things like, A at position ijv equals 6, which looks very imperative and very much in place, and is done actually in place whenever possible. And then we were turning on our multi-threaded backend, and with some applications it went excellent, and other applications just, let me say it frankly, sucked. They were that slow. And we were looking into it, and then we found, well, what is actually happening if I look back at this here? What is happening if all these threads, for some reason, in their local part decide to allocate memory? What happens if they decide to create an intermediate array here? Ooh, they all want to allocate memory at roughly the same time. How does the memory manager deal with that? Well, it says, oh, wait a minute, I'm locking the memory now for thread number X. So actually, the locking mechanism here killed the entire performance. However, if you look closely at the definition of the with loops and how it works, we can actually statically ensure we do know that all local variables that we allocate here are just visible within that thread and nowhere else, because they cannot leave the with loop. Anything that is defined within the with loop cannot leave it. Just the end result gets out of it. So that means we can actually do a very nice trick. we can actually have our own memory allocator, which has now private heaps within the global heap that is accessible for everybody for the individual threads. And whenever a thread individually wants to allocate something, he does it in his own heap without any locking. So then we come to the part that everybody is always asking us, how about the performance? What do you really get out of it? I'm going to show you two benchmarks here. NAS benchmark FT, which is an FFT, a three-dimensional FFT here. And maybe I should have put in a slide where I show the code, because this is like 30 lines of SaC code. Really beautiful, recursive distribution. We cut out arrays and we manipulate arrays very close to the mathematical specification. And anybody of you who has seen the NAS original Fortran 77 code knows that that is a huge difference. Now, what is our performance? We compare essentially here we have the number of processors, and here we have normalized our runtimes to the SaC runtime. So we have almost linear speedups. Well, factor of 6 maybe not be considered almost linear, but I think it is pretty good, given that we really recursively decompose the vectors into smaller vectors. Now, showing these figures is really boring, because what does it tell us to get linear speedup? If my sequential runtime is very slow, then I can always produce linear speedups. So, how do we compare against Fortran? This is now the SaC runtime divided by the sequential Fortran runtime divided by the SaC runtime. That means here essentially that the sequential Fortran program was about a factor 3 to 4 faster than us. However, as soon as we had 4 processors, we outperformed the Fortran 77 version. And we tried auto-parallelizing Fortran 77 compilers. They gloriously failed. So, in a way, I think this is pretty encouraging. In particular, if you compare the source codes, in particular, if you take into account that our source code is like 30 or 40 lines of code, rather than 400 or 500. A better example is NAS benchmark MG. Again, SaC against itself for more processors. Here we have an even better scaling. And if we compare it to the sequential Fortran runtime, to our surprise, we can see that we are actually very close. So our sequential runtime actually is very close to the Fortran 77 runtime. Now, what is the state of the art? Essentially, my sales pitch is, all you need is a C compiler that supports C99. You need to have POSIX threads on your architecture, and you have to have cache coherence or equivalent. So we can't really yet ship data from introduced by the compiler. I know I shouldn't say this. It's always dangerous to announce something in the future. We are since quite a while trying to get SaC 1.0 out of the door, but as we're an academic institution, that is kind of a prolongated, difficult undertaking. However, we have a pre-alpha version which we have just uploaded a couple of days ago on our homepage, so I'd be happy to assist you if you want to give it a try. And we actually have a mailing list where you can stay informed. How much time do I have left? I should finish? Okay. So, what are we currently doing? We actually have the compiler in place from SaC to the micro-threaded with loops. We have all the optimizations essentially done. We can right now map it on operating systems threads, on POSIX threads. All that is in place. What we are currently trying to do or thinking of pursuing is, first of all, we want to compile these micro-threaded with loops into a micro-threaded hardware that is being built at the University of Amsterdam. And we also intend to actually compile this code into more modern processors like the Cell or GPUs or the Cyclops 64. So that is something that we want to desperately look into. Another strand of work that we have started about a year ago is we have actually, for some application, found that maybe the paradigm of data parallelism isn't good enough. Maybe we want to have an alternative means to express concurrency, and that should be streaming essentially. So we have developed an asynchronous stream processing framework that is, however, more or less orthogonal to SaC. So the idea is we have individual stream processing boxes which are essentially SaC programs, and then we can combine these to streaming networks. However, the exchange of the box language, so to speak, is possible. So we have tried to orthogonalize these two as far as possible. All this is part of a European project, the ETHA project on adaptive systems. And the development on SNet is one of the major software components within that project. To conclude, what I'm trying to say is adopting the model of generic array programming is very helpful because it gives us data parallel programming implicitly. So the programmer does not have to be aware of that. And I think this is what a white belt programmer may like. However, to compile that into efficient code is not as trivial as it may seem, in particular if you want to have this high level of abstraction where you have very tiny little data parallel constructs all over the place and you want to aggregate these. So you have to have strong mechanisms to aggregate these. You have to identify methods to actually schedule these, which sometimes is more difficult than it may seem. And last not least, you have to actually be careful how you do your memory management. One of the key things that we have observed while doing all this work is that actually the functional setting is absolutely indispensable. If you want to do this kind of optimization, we would not want to be without the functional setting. So the message that I would like to get across is start thinking arrays, and maybe then you may also like to start thinking SaC. Any further information can be found there. Thank you very much.
You look at me, I'm not a compiler person.
Why are you a compiler person?
No, I'm not. But I only realized, for example, when you cut up the threads and you say you have this data partitioning, very often it is important that, these partitions are not completely independent of each other because at the borders you sometimes have interactions.
No.
Well, shifting left and right meant I cannot believe that the elements on the computation is not always independent.
It is, per construction. You cannot do that.
I'll give you another example. If you have similarity computation in bioinformatics, you have these matrices where you more or less generate the result from the upper left corner to the lower right corner.
But that is not a data parallel operation then.
Well, then you are restricting yourself to a class of problems that might be important, but probably less interesting for the future because the more complex ones.
I'm not sure.
I'm pretty sure about it.
I'd love to have such an application and have a look.
Look at similarity search in bioinformatics. Look at the I always forget the names. The famous similarity algorithms in bioinformatics.
If you do have a data dependency within your algorithm, which is inherent, then yes, you can't define it as a data parallel operation. The question is,
because things spread out more or less in two different streams. If we have in 2 dimensions, one in the direction of horizontally and one vertically.
But if you have this, then you have to. What I'm saying is, the beauty and the beast in itself is this with loop construct. The beauty because it is, I have a guarantee that there is an independence. The beast because if you don't have this independence in your algorithm, you have to rewrite the algorithm.
For example, you had the fold operator where you're summing up things. Yeah. That is not independent. The vector, more or less, you have to add things according to the vector.
Where are we? Fold. Here. This computation is independent.
Yes, I agree. But
the synchronization is just not a barrier synchronization, but I can.
But you see, even with the fold, I believe you can explore parallelism there because the plus is commutative. So
That's actually very nice pass that you're playing over here, because essentially what we have done and what other people do not strictly not like about this design is we say the fold operation here needs to be commutative and associative.
Yeah, because then you can again.
And what we do is we do a logarithmic fold here.
Right.
So yes, we do this.
Okay, good. So fold is therefore, but it is dependent. I mean, you don't look at each element independently. You always have to always group things together. And
yeah, but this happens. I should actually. Yeah, here. But this happens, so to speak, in this barrier. The computation of the individual elements is totally independent.
Yes.
But only when it comes to the synchronization, this is now the fold operation has to be part of the synchronization here.
anyway.
Are you talking about the macro accuracy? That's
No, I'm talking about, because I think if you look at these, if I look at spatially, then I think you sometimes have to be careful how you manage the shape of your boxes in which you aggregate things, because it might be dependent whether or not you interact with many elements on your boundaries or not.
He always creates a new array. So he doesn't overwrite value, but he's writing it in a new array. So the old array just keeps being the same, no matter which you compute. So that's what he means, there is no dependence.
The only interaction you have...
That's a good insight. Okay, you're right. Yeah.
And that's why he says there's no dependence, but there's a new one. And then sometimes you optimize it to actually destructively update the old one, but only if it's provably correct to do so.
Yes.
And the only interaction that you can really have, and I agree on that, is when in the fold barrier. But we consider the fold barrier not to be that computationally intensive.
the first part of the question. Can the programmer express wavefront parallelism? So if I have a matrix I go from one component to the other, there is parallelism on the diagonal.
Yes, you can. It depends. You still have sequential loops in the language, so you can have a for loop.
The loop is sequential, but the inner.
Yeah, that's fine. In a way, again, this happens hopefully without the programmer really noticing, because the operation that he's doing on the way front, hopefully, is being expressed as an array operation. And then you iterate over array operation, and the array operation inherently are then data parallel. And actually, we have found this. We have done this experiment last year where we actually have given this language to a physicist and have said, we will try not to interact with you. Here's the programming language. That's how it works. Write your code. And he has written a beautiful Fortran program in SaC. And what he has done is actually he has written for loops which then iterate over arrays, and you have seemingly destructive updates which we can't conceptually not do as such. However, then he applied the entire thing not to a vector but to a large matrix. So at the end we obtained lots of data parallelism by him just doing generalized selections, by him just selecting entire subarrays without really noticing. Well, computationally he was aware of that, but in a way not to the extent that he was thinking about doing something data parallel on purpose. And it turned out that actually the runtime of that was competitive with the Fortran runtime. So that was a very nice, reassuring experiment that we had there.
You use reference counting completely to determine if you can do destructive updates, or
I would say yes if there wasn't the word completely in your question.
So what I want to know in the runtime, if there's an if tests, right, on the to see is this array singularly used, and then there's special code for destructive and special code for the non-destructive one?
Essentially the answer is yes. However, we try to optimize that away as far as possible. And if you think about it, then essentially the alternatives in the code are minimal, because it's just a matter of how do I get the pointer where to put the result. So either I can reuse an existing pointer, or I have to allocate some memory and give that pointer, and that's it. So it's not that we have to replicate the entire code and have it 2 times there. But we do have a conditional in those cases where we can't statically deduce that we can do it. Yes.
Okay, yeah.
But if you look at the work...
So when you specialize, you only specialize the final call side in a sense.
Yes.
Because the function
Yeah.
can take a parameter.
Yeah, sure.
With the result
Yeah.
pointer that determines
Yeah, yeah,
whether
yeah.
they're destructive or not.
And we actually do, if, for example, if you look at an operation that element-wise adds up 2 arrays, then you actually have 2 possibilities of reusing. And we try to figure out statically which ones are possible or not.
How do you take cache lines into account?
Yeah, we can show it here.
So,
Essentially, we have the freedom to do it in any order. So let's forget about concurrency for a second. So what we do is essentially, if we have this operation defined, then bear in mind the way we have it in the compiler then means we have an identification of the red index set associated with an operation, a green with a green, yellow with yellow. But we try to actually linearize that into the what we call canonical order, that is the order in which it is in memory, because we know that in this order we are going to write it anyways. Now, we have actually had quite successful experiments in analyzing the XSEs that we have. Right? If you see, for example, if you look at a convolution, then you know that you have XSEs 1 row to the left, 1 column to the left, and to the right, respectively. So in these cases, we actually had tiling schemes. So we have a mechanism in our compiler where you can parameterize the compiler by the cache characteristics of the target machine. And when we try to apply tiling. However, I think we would...
It becomes really an issue in the multi-core environment.
Sure. And that's why I'm so excited about this work, which is in a way already...
The freedom to do that.
Because we have the guaranteed freedom to do that. We can actually choose this, and we could have an as smart scheduling algorithm or placement algorithm or whatever you want to use to do that. And I think this is lots of potential that is very difficult to extract from a given C program, if possible at all. So that's why I'm so excited, and I think this actually needs to be exploited now that the multicores are really becoming reality, seemingly.
So other sort of languages have had situations where they've had comprehensions to build arrays. And in languages, particularly those with lazy evaluation, they've often allowed you to name the result and then recursively reference it in the definition, which gives you the ability to do sort of dynamic programming styles of computation. So,
But that would immediately kill the independence.
Well,
yes, it does. Well, it's right. It interferes with static scheduling, right? So it's still functional in nature, but it interferes with your ability to do static scheduling.
Yeah.
But seems like you could still fold it into this framework, except for that caveat.
Yeah, apart from the tiny little aspect that we're intentionally not lazy. Because to have a framework that actually exploit laziness, you need quite a machinery which brings all kinds of problems along, which we have gracefully avoided. Having said that, essentially, if you look at
the laziness is a bit of a red herring.
In the sense of, it's okay to eagerly evaluate it, the semantics allow that. The problem is that the evaluation of one term may require the evaluation of another, and the scheduling of those computations is hard to predict. So
it's not just that. You have memory issues that come along with it, because essentially, if you want to do really lazy evaluation through to the very end, then you have to keep all the contexts. And just imagine you have a sequence of mod array operations, and you don't just want to do them. Then you have pointers to the array. That means for every operation you have to copy things. It turns out to be a nightmare.
I think you're seriously overstating the problem, but that's correct.
Well, maybe I am, but...
So significant uptick in expressiveness and the kinds of things you could describe by allowing sort of wave fronts that process the data. And in many common cases, you could actually analyze the indexing to get back to static scheduling, get back to the question of how do you get wave
But these
fronts?
are distinct issues.
Right.
We were not talking about lazy evaluation. If we talk about lazy evaluation, I think the best argument or the most obvious argument I could pose is look at what Simon is doing, Simon Payton-Jones is doing, and on the to implement efficient array processing. He's putting it into the I/O monad for a very good reason, because there he can actually do things destructively, because there he is not bound to be lazy. And efficiency is very, very difficult if you are fully lazy. Having said that, essentially all these optimizations here are introducing laziness under the hood. Because what we do is, if you, for example, do a take on a very large array, which is defined by a very difficult computation, we don't create this array. We only create those elements that we have in the final result. So in a way, this is introducing laziness through the back door. And in fact, we are looking at some examples where it would be really nice to have some laziness, but we just don't know how to do that without losing the performance in general.
Great, very nice. Thank the speaker again.
Pleasure.